Now we're going to learn a new indirect method of proof called proof by contradiction. So before we get to proof by contradiction, I'm going to give an example of using accommodation in reasoning. We're going to show how accommodation is used to give us a new way of proving statements, namely proof by contradiction. We're going to formally describe what proof by contradiction is, what a proof by contradiction looks like, what its format is. And then we're going to prove a theorem using proof by contradiction. All right, so here is kind of a real conversation I had with one of my kids. I changed the words a little bit, but the gist of the conversation is exactly the same as my oldest kid when he was 4 years old. So he told me, "Daddy, I'm going to play with Xavier tomorrow at school." And then I responded, "Well, Eli, tomorrow is Sunday and you don't have school until Monday. How will you play with Xavier at school?" And once I said that, he just sort of looked at me for a while, and then it's like, oh yeah, of course, I'm not going to be able to play with Xavier at school. Right at that point of the conversation, Eli understood that he was not going to play with Xavier at school the next day. And the important part here is I did not explicitly have to tell him that. He figured it out. Not because he's some kind of genius, but because the logic sort of led him there. So this is an example of something called accommodation. And that is when you believe something, but then you receive some information that contradicts your belief, and then you alter your beliefs, you adjust your beliefs to be consistent with the new information. And this is the kind of reasoning that we use when we do a proof by contradiction. So let's write our sort of the theorem that Eli and I proved and see what a proof by contradiction will look like. That'll give us an idea of the format of the proof, how it's a little bit strange compared to some of the other things that we've proven, but why the logic actually works. So the theorem that we are proving is Eli will not play with Xavier at school tomorrow. Now the first part of our proof, this is just an outline, right? The first part is I let Eli claim that he will play with Xavier at school tomorrow, which seems a little bit weird because we are claiming the exact negation of what it is that we're trying to prove. But that's how it started. Eli says, I'm going to play it with Xavier at school tomorrow. Then I mentioned the fact that tomorrow is Sunday, and then Eli recognizes that this contradicts his claim that he will play with Xavier at school tomorrow. So Eli says he will play with Xavier at school tomorrow. I lead him through some logic that shows that leads to a contradiction, some sort of contradictory claim, and then Eli realized that he will play with it contradicts the claim, and therefore he concludes that he will not play with Xavier at school tomorrow, which completes the proof. Now, if you look at those bullet items as the outline of a proof, it's a very odd format for a proof, not the normal one that we do, and it's hard to match up the things that we're doing in the proof with what actually happens in the theorem. But the most important thing here is the logic is absolutely correct. Logic is airtight. That proof did prove that Eli will not play with Xavier at school tomorrow. So here's what a proof by contradiction is going to look like in general. So we can use a proof by contradiction on literally any statement. Well, we can at least try. In principle, we can. So let's say we're trying to prove some statement. I'll just call the statement P. Here is what a formal proof by contradiction is going to look like. First thing we're going to do is we're going to assume P is false. Another way of saying that is assuming the negation of P is true. And this is what we did when I let Eli assume that he would play with Xavier. The next thing we're going to do is we're going to assume this. We're going to follow this assumption logically until we get to a statement that is clearly false. So where that happened in the proof with Eli is we got to the point where Eli showed that he would be playing with Xavier at school on Sunday, which is impossible, right? That is a logically incoherent statement. And then once we get to that contradiction, we just declare our theorem to be true and the proof is finished. So there's a lot of weirdness in that, but one thing I want to point out that's going to be a particular challenge is the first part, being able to find the negation of our theorem is going to be extremely important in using this. If we negate our theorem incorrectly, we'll certainly won't be proving our theorem with contradiction, And we may even try to prove a statement that's impossible to prove, because if we don't get the right negation, we might be trying to prove a statement that is actually, or might assume a statement that is actually true. Which, again, when you negate it, it should be false. So here's another way of thinking about proof by contradiction. So I like to think of it as a prank that you're pulling on Peeves, which, you know what, after all the trouble that Peeves has given us, totally deserves it, all right? So you tell Peeves that your theorem P is true. Peeves says you are wrong. You respond by saying something like, fine, Peeves, my theorem is false. Then you follow this assumption logically to a clearly false conclusion. So you keep following the assumption logically, which, by the way, Peeves has to go along with, because with all the annoyance that Peeves does, has to go along with logic. So as long as your logic is correct, once you get to a false conclusion, you say, aha, I got you, Peeves. And then Peeves gets mad and then stomps out of the room, and then you just be happy because your theorem is true. All right, so let's try this on an example. Here is a theorem. So we have a and b are integers. If a is even and b is odd, then a squared plus 2b squared is not divisible by 4. That's the theorem that we're going to try to prove. And first of all, before we try to just jump into proving it by contradiction, I want to like at least say to you, this is not an easy theorem to prove directly, right? We don't prove things by contradiction because it's fun to prove things by contradiction, although, you know, if it's fun and if it works, that's fine with me. A lot of times we do these indirect methods of proofs because the direct methods just simply don't work. Proving this theorem directly would be really, really difficult. And the reason why is you're trying to prove that a squared plus 2b squared is not divisible by 4. Prove something is divisible by 4 is very specific and it has like a very real definition, but not divisible by 4, there's a lot of ways that you could be not divisible by 4, and so that makes it very difficult to prove. So we're going to try a proof by contradiction. So what are we going to assume? Well, let's look closely at our theorem. Our theorem is an if-then statement. If a is even and b is odd, then a squared plus 2b squared is not divisible by 4. So remember, we want to say exactly what it means for that if-then statement to be false. That's how we negate our statement. So we're going to assume the negation, which is, well, let's see. For an if-then statement to be false, the if part has to be true, the then part has to be false. So we're going to assume that a is even and b is odd. That's our if part. And then we're going to assume the negation of the then part. So we're going to assume the negation of a squared plus 2b squared is not divisible by 4, which is a squared plus 2b squared is divisible by 4. Okay, so we have three things we're assuming. A even, b odd, a squared plus 2b squared divisible by 4. And another way of saying that, if you want to do it symbolically, is 4 divides a squared plus 2b squared. And then we're going to show, well, we don't exactly know what we're going to show, but whatever it is, it's going to be some kind of false statement. And by false statement, I mean not just a statement that looks kind of fishy, like that doesn't seem right, but a statement that is clearly false, that is obviously false. Otherwise, Peeves is going to give us trouble. So we're assuming that 4 divides a squared plus 2b squared, which means that a squared plus 2b squared is equal to 4k, where k is some integer. Let's see. So we know a is even, b is odd. We're assuming that, right? So a is equal to 2 times an integer, b is equal to 2 times an integer plus 1. Again, those can be different integers, so we use different letters for them. And then probably a reasonable thing to do is take that a squared plus 2b squared and plug in our expressions for those. Then do some algebra, and then we get that. So that's an expression for a squared plus 2b squared. It's equal to that, but it's also equal to 4k. So we're going to go ahead and put those two together. So 4m squared plus 8n squared plus 8n plus 2 is equal to 4k. All right? I mean, it looks fine so far. Let's see if we can find our contradiction. Let's see. So I'm going to go ahead and put all the variables on one side of the equation and just a 2, leave that on the other side of the equation. So we get 2 equals 4k minus 4m squared minus 8n squared minus 8n. And, oh yeah, you know what? No, now that I have all those on one side, the right-hand side, all of those are divisible by 4. So if I wanted to, I could factor out a 4, which I did. And then we can divide by 4. And we get 1/2 on the left side and a bunch of variables on the right side. But all those variables are integers, right? and we're taking integers and we're subtracting them, we're squaring them, we're multiplying by 2. That means on the right I have an integer, and on the left I have 1/2, which is not an integer. So I have an equation that is not integer equals integer, which is a contradiction. That's a clearly false statement. You can't have a number that is at the same time an integer and not an integer. That is contradictory. So yay, there's our contradiction, and our proof is done. So let's go ahead and write the formal part of the proof. The logic is going to be exactly what was on the previous slide. The only difference is we're going to make it much nicer for our reader. And as usual, the first thing we do when we're using a weird method of proof, by weird I mean not direct, is we're going to tell our reader what method of proof that we're using. First thing we're going to do is say, hey, we're going to prove this by contradiction, which means the first thing we're going to do is assume our theorem is false. Because if we just start assuming our theorem is false, our reader might think we're going a little nuts, right? So we're proving this by contradiction, so we're going to assume our theorem is false, which means A is even, B is odd, and 4 divides A squared plus 2B squared. And then we're going to use this to prove a contradiction. So we're telling our reader what we're going to show, not exactly what we're going to show, but again, it's a proof by contradiction. We're going to prove a contradiction, prove a false statement. So we're assuming A is even, so we have A equals 2m for some integer m. We're assuming B is odd, so we have B equals 2n plus 1 for some integer n. We then have, now we're going to plug those in to A squared plus 2B squared. We get A squared plus 2B squared equals 2m squared plus 2 times 2n plus 1 squared. We're going to do the same old algebra that we did before on that. Now we're going to look at the other side. Now we're assuming that 4 divides A squared plus 2B squared, and that means A squared plus 2B squared equals 4k for some integer k. And then we're going to put that together with A squared plus 2B squared equals all that stuff, 4m squared plus 8n squared plus 8n plus 2. We get 4m squared plus 8n squared plus 8n plus 2 equals 4k. Now we're going to play around with, now we're going to isolate the 2 on the left hand side of the equation, and that's what we get. We're then going to factor out the 4, put those together to tell our reader that 2 is equal to that expression with the 4 factored out. We're going to divide both sides of the equation by 4 to give us 1/2 equals k minus m squared minus 2n squared minus 2n. Since the integers are closed under subtraction and multiplication, we're citing our closure properties. And again, if we want to be extra nice to our reader, we could say what we're saying is subtracting and multiplying integers results in another integer. It follows that that expression on the right-hand side is an integer. However, 1/2 is not an integer. Since we have 1/2 equals k minus m squared minus 2n squared minus 2n, and we cannot have an integer equal to a non-integer, this is a contradiction. And since that is what we were trying to prove, now we just remind our reader, hey, that's what we were trying to prove. That means our proof is done. Okay, so that shows you how to use proof by contradiction. Now you are ready for the activities. The PDF that's included with this video is called Proof by Contradiction. Hope it goes well.